Right, so we just talked about how the internal resistance circuit is really a potential divider circuit in disguise. So in exactly the same way as if you turn up this resistance, then it's a greater share of the total resistance, so it'll take a greater share of the battery's EMF. And it's exactly the same in this circuit. If you turn up this resistance, so start with a very high resistance like we did in the experiment, you start with a very high resistance, then across this resistor is then a greater share of the battery's EMF. But if you turn up this resistor, if this resistor is higher, or perhaps you turn down this resistor, so these two are kind of equivalent, then this is going to take a bigger and bigger share of the battery's EMF. But in the internal resistance circuit, that is kind of within the battery. That's the material of the battery itself is providing that resistance. So if this is too small and then these two are kind of similar size, then this will take a significant proportion of the battery's EMF. Because this is a significant proportion of the total resistance. If this is too big, then it's a significant proportion of the battery's resistance and lots of the EMF will be across here. If this is too big, a resistance, then it's a big proportion of the total resistance, so it'll take a big proportion of the battery's EMF. So more of the EMF will be the lost volts as opposed to applied across the external circuit. So that's what happened when you turn down the external resistance. If you turn down the external resistance, then this one is a bigger proportion of the total resistance, so the lost volts is then a bigger share. The lost volts is then a bigger share of the total EMF. Okay, so what we can do is we can just do a final bit of maths relating to that and also relating to the results that we got in the experiment. We can say for the internal resistance circuit, just as for the potential divider circuit, the current in the circuit is the EMF divided by the total resistance, which is R plus R. And if you plot that as a graph, as current as a function of the circuit resistance, well, circuit resistance is on the bottom of the fraction, so it would be like a 1 over x relationship. You'd end up with a graph like this. In fact, actually that graph has a starting point. There's a y-intercept on that graph, and that is exactly the graph we got in the experiment. As we started with a high resistance and turned the resistance down, then we got more current. Okay, that's the easy bit. We could also do the same thing for the terminal potential difference, which of course is IR. So I is this from above, and then multiplied by R means it goes on the top. And if you were to plot that graph, so the terminal potential difference as a function of the resistance, because the resistance is on the top and the bottom, capital R is on the top and the bottom, the shape of the graph actually completely changes. And it looks like this. And you can see that the bigger the external resistance gets, it will dominate over the little r, so you can basically ignore it. If you can ignore it, then the r cancels with that r and you're just left with V term is the full EMF, which makes sense because at the bigger the resistance, this is going to dominate. It's going to take pretty much all of the share, the entire EMF. So that's the maximum value that it would approach. Right, and then the final bit of maths we can do is power, because P is IV. So the power output from that resistor will be the current, which is at the top here, times the potential difference, which is this graph here. And you can see we end up with the EMF squared times the resistance over R plus R, all squared. And that is essentially these two functions combined. Okay, so you can see that at high resistance, what does this graph look like? At high resistance, there's very little current. So if